Intermolecular forces of attraction refers to the forces of attraction between molecules. They should not be confused with intramolecular forces of attraction, which refers to forces of attraction between the atoms that make up the molecule. These two forces of attraction can be distinguished as follows using the molecules of the compound methane. So these are molecules of the compound methane here. This figure on the left shows the covalent bonds that are formed between this carbon atom here and these four hydrogen atoms, and which are responsible for maintaining the integrity of this molecule. These forces that hold the carbon atom to the four hydrogen atoms are called intramolecular forces of attraction. Covalent bonds are relatively strong, but not as strong as ionic bonds. The strength of a covalent bond is approximately 1/5 that of the ionic bond. But of course, covalent bonds have different strengths depending on what atoms are bonded. For example, if hydrogen and hydrogen are bonded together, that amount of energy is released. Let's call it bond energy, or it is an expression of the stability of the covalent bond. The more stable the covalent bond is, we say, the stronger it is. So you can see in this case here, an HH bond is stronger than a CC bond, which gives off that amount of energy when 1 mole of these bonds are formed. A number of factors are responsible for these differences, and one of them is the degree of overlap of the atomic orbitals between the two bonding atoms. Now, if you can recall well, when a covalent bond was formed between two hydrogen atoms, it was the overlap of these orbitals here that created a region between the two nuclei here that was highly negative, and it was that great intensity of negative characteristic that was developed there that was responsible for bonding these two nuclei together. See, as you said, these negative charge would attract these positive charges on the nuclei there, and that is what creates a covalent bond here. So definitely, if you have a greater degree of overlap here, a greater amount of negative charges will be created here to attract these positive nuclei here. That's why, depending on the degree of overlap, that will determine the strength of the covalent bond that is formed here. All right. We'll now talk about the intermolecular force of attraction. These here are called intramolecular forces of attraction, and those refer to the covalent bonds that are holding the atoms within a molecule. However, the intermolecular forces of attraction are those that attract molecules of the same compounds together. If you're using methane to illustrate this, we're talking about the forces of attraction between methane molecules here. Intermolecular forces of attraction are of two types, and together they're called van der Waals forces of attraction after Johannes van der Waals. In 1873, Johannes van der Waals attributed the attraction of molecules of gases to each other as a deviation from the ideal gas model. We have not done the ideal gas model as yet, but some of the properties of the ideal gas are as follows. One, it is believed that the molecules do not have any volume. Two, the molecules do not attract each other, nor are they attracted to the walls of the container in which they are placed. Johannes van der Waals believed that gas molecules themselves have infinitesimally small volumes compared to the volumes that they occupy, and that they attract each other. Two forces of attraction between molecules have been identified, and these are dipole-dipole forces and London dispersion forces. What are dipole-dipole forces? Polar molecules, as can be recalled, have bond dipoles. And if two of these molecules are close enough together, they will attract each other. This happens when the partial positive charge on the end of one molecule is attracted to the partial negative charge on the end of a neighboring molecule. So you can see here, this is one molecule here with its bond dipole, and there's another molecule here with its own bond dipole, and you can see that the positive end here of this one here is attracting the negative charge on the other molecule there. The attraction between the dipole of one molecule and the dipoles of other molecules is called dipole-dipole forces, states of matter and intermolecular forces of attraction. For molecular compounds, it is the magnitude of the van der Waals forces between the molecules that determine their states. In solids, because of the large magnitude of intermolecular forces of attraction between the molecules of the same compound, they exist as solids. In these, the molecules align themselves in regular patterns since they're held very strongly. And of course, these will have higher melting and boiling points. This picture here is depicting for us how all these dipoles here are aligned in regular patterns, and that's attributed to the strong forces of attraction between these neighboring molecules. And a lot of it has to do with the strength of the dipole-dipole forces between these. And of course, something that you'll be doing later on is called London dispersion forces. So because of that great magnitude of the dipole-dipole forces, or generally speaking, the high magnitude of the van der Waals forces, some molecular compounds exist as solids. On the other hand now, if the van der Waals forces of attraction are relatively weak, then the compound will exist as a liquid. In this case, the dipoles will be arranged in all different directions. You can see it as depicted by this diagram here. There's no regular pattern in which they're arranged, and therefore the molecules can slip and slide, and that will make them attain the shape of the container in which they are placed. This brings us to London dispersion forces. Empirical evidence shows that nonpolar molecules such as methane and carbon dioxide, when cooled to very low temperatures, become liquid and solid respectively. These observations indicate that there is considerable amount of forces between the molecules at low temperatures. Since these molecules do not have any charges on them to attract each other as happened in polar molecules, what could account for their attraction? The answer was provided by German physicist Wolfgang London, 1900 to 1954. He explained that since the electrons in molecules are in constant motion, and if they were to be frozen at any time, it will reveal that their distribution over the molecules will be non-symmetrical. This indicates that electrons swarm more to one side of a molecule than the other at any given time. This tendency of electrons in a molecule to do this describes its polarizability. As a result of this constant non-symmetrical distribution of electrons over a molecule, an instantaneous dipole is created on it. A small negative charge is created on one end of the molecule, and a small positive charge is created on its opposite end. This is illustrated in the figure here. This figure depicts how an instantaneous dipole is created in the molecule. As the electrons swarm to the right side of this molecule here, a small negative charge is created there. Because of this shift of the electron from this side of the molecule to the other side, to the right side, the positive nucleus, this positive nucleus here, manifests itself as a small positive charge on this left side of this molecule. This happens in an instant, and it is temporary. It is said that an instantaneous dipole is created on the molecule. Induced dipole. If a molecule, like this one here, with its instantaneous dipole, is next to a neighboring molecule, it induces a dipole on it as illustrated in this figure here. As you can see here, the electrons on this side of this molecule here repel electrons away from this side of the molecule to that side there. As a result of that, this positive nucleus here is isolated and thus manifests itself as a small positive charge on this side of the molecule. And because a dipole is now induced on this molecule here, where you're having this small negative charge on this side of the molecule facing this small positive charge on this side of the molecule, there's some degree of attraction here. And this is what is responsible for attracting nonpolar molecules together. So he said that these forces are short-lived, appearing and disappearing continually with lightning speed. Intermolecular force of attraction and boiling point. This table here shows the relationship between the masses of nonpolar compounds and their boiling points. In this column here, you're seeing examples of the nonpolar molecules. All of these molecules here are nonpolar, as can be recalled. These ones here are homonuclear diatomic molecules. This one is tetrahedral molecule, and this one is a linear molecule. We have done these molecules already, and we have seen how they're all nonpolar here. As we move from bottom to top, the molar masses of the compounds increase in that direction. And there appears to be now a relationship between the increase in boiling point and the mass of the compound. Look, the lighter the compound, the lower is its boiling point. As the compounds become more massive, you can see that the boiling points increase as you move in that direction there. Iodine with the greatest molar mass has the highest boiling point here when compared with hydrogen with the least molar mass and the lowest boiling point here. There also appears to be a relationship between the boiling points of these compounds and the number of electrons in their molecules. So why do you think that is so? This could be so because as the number of electrons in molecules increases, so do their polarizability. That means that greater instantaneous dipoles can be created. You have a greater swarming of electrons from one side to the next. You have greater induced dipoles in neighboring molecules, and therefore you have greater intermolecular forces of attraction. And obviously, you're going to have higher boiling points for these types of compounds that have larger number of electrons. All what I said is contained in these paragraphs here, okay? Another factor to take into consideration about the boiling points of compounds, apart from its number of electrons, it is the shapes of the molecules. In organic chemistry, you'll be taught about isomers. These are compounds having molecules with the same formula, but different shapes. As you can see here, the molecules on the left are spherical in shape. So because of this spherical nature, they have less surface area facing each other to induce dipoles on neighboring molecules. Of course, this compound here will have a certain boiling point. However, the molecule on the right, as you can see, are oval-shaped and are thus having greater surface areas facing each other to induce bigger dipoles on neighboring molecules that results in greater intermolecular force of attraction between these molecules than these one here, and therefore expect these to have higher boiling points. Are London dispersion forces also present in polar molecules? The data in the following table will show us. This column here shows 3 hydrides with their respective molar masses. As you can see, their molar masses increase from bottom to top. This column here shows their electronegativity differences. Based on the data shown here, which one do you think is the most polar one? Obviously, the molecule that has the greater electronegativity difference between the two bonded atoms should be the most polar one. And in this case, it should be hydrogen chloride molecule followed by hydrogen bromide molecule. And this molecule is said to be nonpolar because the difference in electronegativity between the hydrogen and the iodine there is only 0.4. It should be greater than that to be deemed polar. So based on what you're seeing here, which is the most polar molecule? Again, we should say it is the hydrogen chloride molecule because of this big difference in electronegativity compared with those two there. Which one, therefore, you should expect to have the highest boiling point? It should be the compound where the molecules are having the highest polarity. If you say that you expected hydrogen chloride to have the highest boiling point, then you are correct. But look, see, look what is happening here. We can see the reverse is happening here. Look at the boiling point for hydrogen chloride. It is negative 85. That for hydrogen bromide is negative 67, and this one here is negative 36 degrees. So you can see as you move from bottom to top, there's an increase in boiling point. So it is opposite to what we expected. So how do we explain this anomaly? It all has to do with the large increase in London dispersion forces between these molecules here. See this? As you move from bottom to top, because the molecules are increasing in molar mass, there's a big increase in London dispersion forces. And it will appear, therefore, that the gain in London dispersion forces overwhelms the dipole-dipole forces. The London dispersion forces that are gained by hydrogen bromide and hydrogen iodide are more than dipole-dipole forces between the hydrogen chloride molecules. So what can we conclude from that? Look, both of these molecules here are polar, but we can see that this one is having a higher boiling point than this one, all because the molecules are attracting each other by greater London dispersion forces. We can safely say that polar molecules are not only attracted by dipole-dipole forces, but also London dispersion forces. All of that is given in this paragraph here. You can pause the video and read that. We will now discuss the concept of hydrogen bonding. Hydrogen bonding is a special type of attractive force between the hydrogen atom covalently bonded to a highly electronegative atom, such as oxygen, nitrogen, or fluorine, and a lone pair of electrons on a highly electronegative atom on the same molecule, as happens in protein molecules, or in a neighboring molecule. It would appear that only certain elements are capable of creating hydrogen bonds when they react with hydrogen. And these are oxygen, nitrogen, and fluorine. It is said that these atoms are small and electronegative enough such that when they bond with hydrogen, they create a highly polar bond with it. And when that happens, it makes the hydrogen on the molecule acquire a small positive charge. Let's unpack this by looking at the water molecule. So here is your oxygen atom. This is said to be a highly electronegative atom, and it is bonded to these two hydrogen here. Because of this high electronegativity difference between the hydrogen and this oxygen here, this hydrogen here acquires a small positive charge. Both of these will acquire small positive charges. Now, this is what happens. Because of this small positive charge here on the hydrogen atom, is attracted to a lone pair on a neighboring molecule here. So if you have another water molecule here, you can see this oxygen here is having two lone pairs of electrons. And because they're also highly negative, this hydrogen here will be attracted to that. And this bond between this hydrogen and this pair of electrons here is called hydrogen bond. This is how hydrogen bonds are formed. These are the two examples to show you again how hydrogen bonds are formed. Of course, we've spoken about this already, how this becomes slightly positive here, and it can bond with a lone pair on a neighboring molecule, such as ammonia here. This is one of the reasons why ammonia is so soluble in water, because of the numerous amount of hydrogen bonds that can form with water. This other example here shows how a hydrogen bond is formed between the hydrogen from water molecule and the lone pair from this hydrogen fluoride molecule here, okay? So note, these are the only three elements here that can form hydrogen bonds. All right, just come back a little bit to this figure here. See, these hydrogen bonds here are what are responsible for holding the water molecules together. You can see that. How does water evaporate? Water evaporates when these molecules here gain enough energy to snap their hydrogen bonds and escape. Of course, you know, as water gains more energy, if you raise the temperature of water, the rate at which evaporation takes place is greater there than when the temperature is low, because when you raise the temperature, these molecules are gaining more kinetic energy to vibrate away from each other, and eventually this bond snaps and allows the water molecules to evaporate. Do we have evidence for hydrogen bonding? This table here shows what would normally be expected from these hydrides here. These are the hydrides here. These are the molar masses here. So you'll expect that as the molar masses increase, the London dispersion forces between their molecules increase. And because of this gain in London dispersion forces, you can see there's an increase in their boiling points as you go downward. That is, this one will have a certain boiling point here. This will be higher than that one, and this will have the highest boiling point. No problem. Everything is normal here. Let's look at this other table now. I leave that so that you can come back and read that later on to see the explanation that I've given there. Okay, you can pause the video and watch that. But let's look at this table now. Here we have two hydrides. This is hydrogen sulfide with a molar mass of 33.08 grams per mole. And this is water here with a molar mass of 18.01. Based on this previous table, the boiling points increase as the molar masses of the compound increase in that direction there, right? So following that logic, which one here you expect to have the higher boiling point? The one with the higher molar mass. Is that what happens? Let's see. See that? This has a boiling point of negative 60 degrees Celsius. There's a difference of 160 degrees between the boiling points of hydrogen sulfide and water. How do we account for that? It is because water molecules are able to form hydrogen bonds, unlike these ones here, which are not capable of forming hydrogen bonds. They combine London dispersion forces, and that due to hydrogen bonds makes this have a higher boiling point than this one. So this is the evidence for the presence of hydrogen bonds. You have a few questions there for you to do. Testing for polarity. So if you have a compound in the form of a liquid and you want to know if it is polar or not, what you do is this. You take a stream of that liquid and you bring a charged rod next to it. It could be either a positively charged rod or a negatively charged rod. If it is attracted to it, then the liquid here has polar molecules. If it is not attracted to it, it is a non-polar compound. This figure here shows how a fine stream of water is attracted by both a positively charged rod and a negatively charged rod. And this happens because water is a polar compound. When water is placed next to a positively charged rod, it causes the molecules of the water to orient themselves with their negative ends pointed towards the rod. And when that happens, because of these opposite charges here, the stream of water is bent towards the positively charged rod. On the other hand, when it is placed next to a negatively charged rod, the water molecules reorient themselves in such a way that their positive ends are attracted to the negative rod. And that's why in both cases here, stream of the water is bent towards the rods. In case of a non-polar compound, such as carbon tetrachloride, because they do not have any small charges like what these have here, they will not be attracted to either a negatively charged rod or a positively charged rod. That's how you can distinguish between a compound in its liquid form, if it is polar or non-polar. Bring it next to a charged rod. If it is attracted to it, then it can say it is polar. If it is not, then we can say it is non-polar.